Besides the primary reason of reducing friction, there are secondary reasons for having a lubricant within the engine. Even if the engine was kept scrupulously clean, there will always be small amounts of dirt or impurities that find their way inside it. That dirt must be removed from the oil before it can cause damage to bearings or block small oil passageways within the engine. The oil keeps the interior of the engine clean by carrying any contaminants in suspension in the lubricant to the oil filter, where they're removed. The majority of the bearings within the engine are manufactured from steel, a metal which would soon oxidize itself if it were not prevented from doing so by a liberal coating of oil. Thus the lubricant also minimizes corrosion inside the engine. The bearing surfaces in the engine, particularly those towards the turbines, must be cooled if they are to be able to withstand the constant heat stresses imposed upon them. The lubricant is used to take the heat away from the bearing surfaces and transfer it to the oil cooler, where it's dissipated into the atmosphere. A further task of the lubricating oil is that of being a hydraulic fluid. For instance, in some turboprop engines, the control of the pitch of the propeller blades is achieved by using the engine lubricating oil to operate the pitch change mechanism. Most gas turbine engines use a self-contained recirculatory lubrication system in which the oil is distributed around the engine and returned to the oil tank by pumps. There are two basic recirculatory systems which we'll investigate here. They are the pressure relief valve system and the full flow system. The pressure relief valve, which gives its name to this type of lubricating system, is situated in parallel with the oil pressure pump. It limits the pump outlet pressure by diverting any excess volume back to the inlet of the pump, thus controlling the flow of oil to the bearing chambers. The engine oil pressure is restricted to a value which the engine designer considers correct for all conditions that the engine might encounter. The pressure relief valve will begin to relieve pressure at the value which is generated by the oil pressure pump at engine idling speed. As a consequence, the pressure relief valve theoretically maintains a constant pressure over the whole of the engine's speed and oil temperature ranges. This diagram shows the basic components required in the pressure relief valve lubrication system of a turboprop engine. The oil is drawn to the pressure pump through a suction filter. The suction filter protects the pressure pump from damage should any debris enter the tank. The oil pressure pump is contained within an oil pump pack. The oil pump pack contains one pressure pump and several scavenge pumps. Having several scavenge pumps ensures that the lubrication system remains a dry sump system. From the pressure pump, the oil is passed through the pressure filter, which removes any small particles which may block the feed jets. The oil then flows to the pressure relief valve, which maintains the oil pressure to the feed jets in the bearing chambers constant. The oil is passed to the feed jets through internal drillings and external oil pipes. In this particular engine, the hollow interior of the compressor turbine shaft is used to transfer oil from the front of the engine, where it's used in the pitch control mechanism, all the way through to the rear of the engine, where it's used to lubricate and cool the turbine bearings. The torque meter pump shown in this diagram is used to boost engine oil pressure to a figure which is considerably higher than normal system pressure. In some turboprop engines, the torque meter pump output can be as high as 600 pounds per square inch. Torque meter pressure is utilized to balance the axial thrust of the helically cut gears within the propeller reduction gear. The axial thrust is proportional to engine power output. When the oil has completed its task of lubricating, cooling, cleaning and acting as a hydraulic medium, it falls into collecting trays or compartments from where it makes its way to the scavenge pumps. The scavenge pumps push the oil through an air-cooled oil cooler, where the heat is dissipated into the atmosphere. From the oil cooler, the oil travels to the de-aerator tray, where any air bubbles, which will have been formed in the oil, escape, and the oil falls to the oil tank, which in this case is contained around the engine intake. Any air pressure which has been built up within the engine lubrication system, through leakage from seals or from the de-aerator tray, must be allowed to escape. If the air pressure was just vented to atmosphere, then any oil mist contained within it will pass to atmosphere also. Thus the oil contents would quickly diminish. To prevent any loss of oil occurring in this manner, the oil mist is vented via a centrifugal breather, which is fitted to and driven by the accessory gearbox. The full-flow lubrication system achieves the required oil flow to the engine throughout its entire speed range by allowing the oil pressure pump to supply the oil feed jets directly, without the use of a pressure relief valve. Using this type of system allows the use of smaller pressure and scavenge pumps, since the volume of oil passed by them is less than that which is passed by the pumps in the pressure relief valve system. This discrepancy in the volume of oil used in each of the two systems exists because of the large amount of oil which is spilled back, either to the oil tank or the inlet of the pressure pump, in the pressure relief valve lubrication system at high engine speed, whereas no excess pressure is generated in the full flow system. The pressure pump picks up oil from the oil tank through a suction filter. The high-pressure oil generated by the high-pressure pump passes through a pressure filter to the distribution galleries. Fitted across the pressure filter is an oil differential pressure switch. The oil differential pressure switch will give a warning of filter blockage. This warning is usually indicated at the ground crew servicing panel, and is sometimes duplicated by a warning light on the flight deck. The upper portion of the oil gallery transfers the oil to an oil pressure transmitter and low oil pressure warning switch. These items are used primarily to give warning in the cockpit of malfunctions in the oil system. Other parameters indicated in the cockpit are those of oil quantity and oil temperature, the latter being measured as the oil leaves the oil cooler. A tapping from the upper portion of the gallery transfers oil to lubricate all of the bearings in the accessory drive gearbox. The lower portion of the gallery is used to transfer oil to the bearings which support all of the compressor spools. The bearings are lubricated by oil jets, which are positioned very close to the bearings. This minimizes the possibility of the oil being deflected from its target by local turbulence. Thread-type filters are fitted in the oil supply line just before the oil jets. Thread-type filters perform the function of a last-chance filter, removing any debris which may have managed to pass through the main pressure filter. In a similar manner to the pressure relief valve system, when the oil has completed its tasks, it's collected by scavenge pumps. Prior to the oil reaching the scavenge pump, it passes over a chip detector and through a suction filter. The scavenge pumps pass the oil to the oil cooling system. This engine utilizes two types of oil cooler, a fuel-cooled oil cooler and an air-cooled oil cooler. Normally the fuel-cooled oil cooler is sufficient to cool the oil on its own, but in the event that it proves inadequate, a valve opens automatically and brings the air-cooled oil cooler into operation as well. We mentioned earlier that air pressure escaping from seals cannot be allowed to build up within the engine. In this engine, air pressure within the engine is vented through the hollow shaft of the drive between the intermediate gearbox and the external gearbox, leaving the external gearbox via the centrifugal breather. The oil tank is normally a separate unit mounted on the side of the engine, although it can be part of the engine intake, or even an integral part of the accessory drive unit. Whatever form the oil tank takes, it must incorporate provision for filling, either by gravity and or more normally from a pressure source. There must also be some method of determining the contents of the tank, either by a sight glass or by a dipstick. Sometimes both methods are used. A de-aerator tray removes air bubbles from the oil as it flows back into the tank.